SDR or software defined radio. So this is a very important concept in communication technology. So we will be taking MCQs, multiple choice questions on SDR, the cognitive radios and the legacy radios. The content has been taken from this resource, but there are various resources which can provide you this free material open to all. What is a software defined radio? SDR. Now what is this SDR? The options we have, first is radios can be reconfigured on the fly. The second option is can be quickly and easily upgraded. Then we have can listen, talk to multiple channels at the same time. Then we have the final option, new kinds of radios can be built. The final option is all of the above. Now the correct answer which you are judging perfectly is all of the above. Now this SDR or software defined radio, in a radio communication system, it is a radio that uses software to process signals. So software is employed wherever it is possible. Everything will not be in hardware as in the previous times. That is when the radios were new to the market. The old legacy radios, you can just tune to different frequencies and that frequency range is also limited. And most of the parts of the radio you cannot change. That is, it's not configurable. There was a very small HMI, only few things can be changed. But if you want to change the waveform, the modulation scheme, the filtering, then we can change it in the software defined radio using the software. So software defined radio is a type of radio communication system where the components that traditionally were implemented in hardware, that is these components can be mixers, filters, amplifiers, modulators, demodulators. So they are implemented in software rather than the hardware. So it's all about the softwareness or putting things in software in a radio. So what is the benefit? So this allows for greater flexibility as the functionality of the radio can be changed simply by updating the software. Just changing or updating the software will work. So SDR replaces traditional radio hardware components with the software, allowing for digital processing of radio signals. So this digital processing of radio signal is possible here, and this technology, this SDR, enables the implementation of various radio modes and signaling technologies using the same hardware. That is, I'm talking about the signaling technologies in the mode that can also be implemented using the same hardware, thus offering the flexibility and quick reconfiguration capabilities. SDR features can be changed by first option in this, that is the SDR has different attributes and features. So that can be changed by first is changing hardware and software. The second option is changing these function specific software only, changing the monitor program or changing the controller. Now in these all options, what is the correct option? Yes, it's software, changing the specific software. So SDR features can be changed by changing function specific software only. Now this SDR or software defined radio, this is a radio communication system that uses software to process the signals. Most of the things, the component, hardware component, they are implemented in software rather than the hardware. So SDR features or attributes, how can they be changed? So just the specific software part or software code can be changed, and since the different parts, mixers, filters, amplifiers, modulators, demodulators, they are mostly implemented in software, so you can just change it, right? So SDR replaces the traditional radio hardware components with software, allowing for digital processing of radio signals. So the software defines the radio signal processing and communication protocol also, and which includes what all you can change, because this SDR features can be changed by reconfiguring the software. So carrier frequency can be changed, signal bandwidths can be changed, modulation scheme can be defined. It can be PSK, QPSK. Network access, how the network will be accessed. The cryptography, you want to safeguard your data, safeguard your communication. For that, cryptography can be done. The error correcting schemes like error correction coding can be applied. And also voice, video and data is becoming so important. So the source coding of voice, video and data can also be performed. So this is how SDR features can be changed. In software programmable radios, the parameters which can be controlled are, so in the software programmable radios, what are the parameters which can be controlled? The first one is volume, channel number, modulation scheme, and finally 1 and 2. So it can be volume, channel number and modulation scheme together also. So if the fourth option would have been 1, 2, 3, that option also would have been correct. So I am suggesting all of them can be true. So option number 4 can also be 1, 2, 3. So SDR features, we are talking about the parameters, and that can be controlled. All the parameter mostly can be controlled in SDR. So SDR stands for software defined radio, which are radio communication system that uses the software to process signal. So this software defined radio is a wireless device that uses software to control the radio's properties, radio's parameters and attributes. So the software also performs the signal processing in a general purpose computer, or it may be a digital electronics. So this all carrier frequency till source coding of voice, video or data can be done because the parameters are controlled by software. In SDR, the communication technology is provided by. So the options are, first is DSP, digital signal processors, FPGA, field programmable gate arrays, GPU, that is graphics processing units, and finally we have all of the above. Now there is one more option which is missing, which is general purpose processors, GPPs. So you might be thinking FPGA is the correct answer, but let me tell you, the fourth option, all of the above, is the correct option. So whenever we talk about SDR or software defined radio, so this is a kind of communication technology where we use the software to process signals, and the components like mixer, filter, amplifier, modulator, demodulator, they are implemented in software rather than hardware. So when we talk about the computation, in a normal computer system we have different processing system, that is the high visualization is a work of the graphic processor. In this SDR, the general purpose processors, GPPs, the DSPs, digital signal processors, the field programmable gate arrays, FPGAs, all these are used for the computation. So we are talking about computation technology. So all these four will come. So all of them are the correct answer. The channel capacity depends on. So we are talking about Claude Shannon. Now what option do we have? The first one is the SNR, signal to noise ratio. Then we have the bandwidth. Then both. And finally we have none of these. So you got it right. The answer is both, which is option number 3. So this channel capacity, what exactly is this? So this channel capacity is all about understanding, like a road is there. How many cars can run on the road simultaneously? That is the capacity of that channel, the capacity of that road. It can contain how many vehicles? Same way, the channel capacity is the maximum rate at which information can be transmitted through a communication channel per unit of time, taking into account the signal to noise ratio SNR and the channel bandwidth. So how much of data for a particular time the channel is able to contain is called the channel capacity. Now signal to noise ratio and bandwidth, they both have become very important. Claude Shannon, the great gentleman, he told us, or he gave us, this Shannon-Hartley channel capacity formula. In this channel capacity formula, first thing comes is the channel capacity, and we have a B also, which is the bandwidth. C is the channel capacity in BPS. So let me write it. C is the channel capacity of bits per second. So this is determined by number of distinguishable intervals per second and the number of bits per interval. For the information theory, it is a key attribute to information theory, and it is measured in bits per second. So this channel capacity which I just mentioned, this is given by a certain formula or depending on directly proportionality or the inversely proportionality. So this B will be the bandwidth of the channel in hertz. This log is base 2, you know already that. What does this mean? And inside this we have 1 plus S by N. This N is the average power of the noise and the interference over the bandwidth, which is in the watt. And S is the average signal power over the bandwidth, again in the watt terms. So we call it as a signal to noise ratio or carrier to noise ratio, CNR, SNR or CNR. So C will be in bits per second, B will be in hertz, S and N will be, actually S by N is a dimensionless quantity, SNR. A carrier frequency of 800 megahertz is modulated by a 1 kilohertz signal. SDR requires Nyquist sampling rate of 2 into 800 megahertz. The options are: first is 2 into 800 megahertz, 2 into 1 kilohertz, 2 into 800 megahertz, and 2 into 800 kilohertz. Now what you see here is 2 into 800 megahertz has come twice. You can just choose one of the option. Now what is the Nyquist theorem? What does it say? So Nyquist sampling rate or theorem says that an analog signal can be digitized without aliasing error. So what is the this aliasing error? Now if you want to convert this analog to digital, and this is the analog, okay, this is the above the corner hits, or these are the distortions you can say. So this will create the aliasing error. So the sampling rate, Nyquist theorem said, this analog digital can be digitized without aliasing error if and only if the sampling rate is greater than, or equal to, it can be greater, it can be either equal to twice the highest frequency component in a given signal. So if you want to understand using the formula, this C is equal to 2B log M, the base is 2. What is C here? C is the capacity in bits per second, BPS. Now this capital B which you are witnessing is the frequency bandwidth in hertz, and M is the number of levels a single symbol can take on. So it can be 1, 2, 3, multiple levels, you know about that levels. So this idealized capacity equation, it represents or shows us that the data rate is proportional to twice the bandwidth and logarithmically proportional to M. So this data rate, which is the 2 times bandwidth, and the SR, which is the sample rate, are related like this. This is what Nyquist theorem is talking about. Now when you use this formula and you are being said that the carrier frequency is 800 megahertz modulated at 1 kilohertz. So you know by Nyquist theorem it has to be 2 into 800 megahertz, and you don't have to worry about log M because 1 kilohertz is given. So 2 into 800 megahertz is the solution for a carrier frequency of 800 megahertz is modulated by a 1 kilohertz signal. This is the sampling rate. In a transmitter block, an SDR requires, so this first one is both ADC and DAC. ADC stands for analog to digital converter. DAC stands for digital to analog converter. So both are required, only ADC, only DAC, or finally no ADC or DAC. So what is the correct option? Yes, you got it right. It is the first one, which is both ADC and DAC. So this SDR software defined radio is a type of radio communication system where the components that traditionally were implemented in hardware, for example the mixers, the filters, amplifiers, modulator, demodulators, they are implemented in software instead of hardware. So whichever SDR you will talk about, there will be a transmitter TX, there will be a receiver RF. So when we talk about the transmitter system, that is the one part of the system where the transmission takes place. Here what all is done? Signal generation and modulation, which is done in the software. Then we have the DAC, digital to analog conversion, which you see here also. Then the RF up conversion, that is in order to move the signal to the desired frequency which is required. RF up conversion is required. This is how it is being done. A carrier frequency is used with the original signal. That is how it is being modulated and being sent. Then the power amplification, that's to strengthen the signal, and the filtering in order to clean the signal. And finally the antenna, because we need to transmit the signal, that is sending it to RX. We need TX antenna, and in the RX also we need an antenna to get the data, to receive the data. So these elements, they are together allowing this SDR to transmit signals over different various bands with flexible modulation schemes. FPGA allows. Now FPGA is field programmable gate array. So what all it provides, FPGA? We can do the parallel addition, parallel multiplication, both or none of these. Yes, you got it right. The answer is both 1 and 2, which is the correct option, option number 3. FPGA is a field programmable gate array. So what is this? This is an integrated circuit that can be reprogrammed to perform specific functions after it's been manufactured. It has been manufactured. And you can also do the field programming, because FPGA's ability to program in the field also after it's being released by Xilinx. So FPGA, this can be serial, this can be parallel. So FPGAs allow both parallel addition and parallel multiplication, as they are often used to implement such operation efficiently due to their parallel processing capabilities. So let me explain this with an example. The first is matrix multiplication. So in matrix multiplication, many individual multiplication and addition operations, they occur in parallel. So FPGAs are excellent for implementing this due to their ability to handle multiple arithmetic operations at once, making them ideal for tasks like the neural network processing, where matrix multiplication is critical. One more example is the fast Fourier transform. The signal processing, for example, in the signal processing task like the FFT, which is the fast Fourier transform, the FPGAs can perform many multiplications and additions in parallel, thus greatly accelerating the computation speed compared to the CPUs, which is the central processing unit. So that's how the FPGA allows both parallel addition and parallel multiplication, because they have this parallel processing capabilities. Cognitive radios can. So there are different kind of radios. We have software defined radio, we have legacy radios, we have these radios, the cognitive radio. So cognitive radios are intelligent radios. So these are advanced radio systems that have the ability to do certain things. Sense free spectrum, can locate transmit stations, can use AI, all of the above. What is the correct answer? It's an intelligent radio. So the answer is correct. It's option number 4. So these cognitive radio or CRs, these are those advanced radio systems that have the ability to automatically adjust their transmission and reception parameters in order to optimize the spectrum usage. So you can call these cognitive radios are as intelligent, as smart, as on the fly changing capability cognitive radios. So if the radio can change or can modify its own parameter in order to optimize the spectrum usage, it's cognitive radio. So it's a smart radio. So if we have many, the road is blocked, then it can be shifted to a road where the traffic is less. So that can only be done when the radio is cognitive, self-understanding. So the dynamic spectrum access can be done by cognitive radios. Spectrum sensing is also a possibility. It's what CRs are doing. The adaptive transmission is possible. The interference avoidance is being done by the cognitive radios. Learning and decision making is one of the operation. The cooperative communication can be done. Enhancing the network performance is also a possibility. And support for multiple standards is one of the tasks. Also, the different standards and the regulatory changes are coming up. So much support for this multiple standard along with the real-time adaptation to regulatory changes depending upon the government, depending upon the country. So these all can be done by the cognitive radios. In SDR, the ZIF stands for ZIF. So first is zero insertion force, then we have zero intermediate frequency, zero insertion frequency, and none of these. So the correct answer is the option number 2, zero intermediate frequency. Now what is ZIF in software defined radio? This ZIF is standing for zero intermediate frequency. So let me tell you what exactly this intermediary frequency is. In communications and electronic engineering, an intermediate frequency IF is a frequency to which a carrier wave is shifted as an intermediate step in transmission or reception. So the intermediate frequency is created by mixing the carrier signal with a local oscillator signal in a process called heterodyning, resulting in a signal at the difference or beat frequency. So this is the diagram which is partially showing what I'm talking about. So here we have the local oscillator signal. So the carrier signal is mixed with this local oscillator signal, which is the process called heterodyning. And this results in a signal at the difference or a beat frequency, which you see here. This ZIF, zero intermediary frequency, this is actually a radio architecture that converts a received radio frequency RF signal directly into the baseband signal. So it converts RF to baseband signal without using intermediary frequency IF stages. The BER here stands for bit error rate or bit error ratio, BER. The options are is directly proportional to SNR, inversely proportional to SNR, is not related to SNR, none of the above. Now the correct option is option number 2, inversely proportional to SNR. So the bit error rate or bit error ratio is the number of bits errors per unit time. Because BER and SNR are inversely proportional, so let us understand the BER and SNR first. So they are inversely proportional. First of all, if SNR will increase, BER will decrease. If BER will increase, SNR will decrease. And this is vice versa. What is BER? Bit error rate is the number of bits errors per unit time, or the bit error ratio, which is also known as BER, is the number of bit errors divided by the total number of transferred bits during a studied time interval. So how many are being sent, how many were in error, the ratio is this one. So this bit error ratio is a unitless performance measure, and it is often expressed as a percentage. For example, 10 bits are being sent here. All of them have been received, but one was with error, which this is the 0 one. So the received one which have the error, which is 1, divided by the sent bit, which is 10, this is called the bit error rate. When we talk about the SNR or signal to noise ratio, in analog or digital communication, a signal to noise ratio, often written as S/N or SNR, is a measure of the strength of the desired signal relative to the background noise, which is the undesired signal. So this is the measure of signal strength, which is represented as a ratio along with the noise level or noise floor existing. So the signal strength divided by the noise strength is SNR. So the bit error rate BER is inversely proportional to signal to noise ratio. This means that as the SNR increases, the signal becomes stronger relative to noise. The BER is going to decrease. That means fewer or lesser errors occur during data transmission. So now you see this diagram. This directly shows the diagram or the graph between bit error rate and the signal to noise ratio. So the lower SNR leads to higher BER, as more errors are likely due to increased noise in the signal. So when bit error increases, the SNR will decrease. When the SNR will increase, the bit error will decrease. So they are inversely proportional to one another. In ADC, the correct sequence is ADC stands for analog to digital converter. Options are sampler quantizer encoder, quantizer sampler encoder, encoder quantizer sampler, and the order is variable. So the correct option is the first option, sampler, quantizer and encoder. Now in the analog to digital conversion, the whole idea is to convert the analog signal into the digital signal, that is the sine wave, into 0101. For this, in analog to digital converter, the correct sequence is sampling, then quantization, then encoding. That is, the processor actually converts the analog signal into digital signal, and that can be processed by the digital systems because analog signals cannot be processed by a digital system. So you have to convert this analog coming signal, which is the actual signal, into digital conversion. So what do we have? How do we do this? Sampling. So in this sampling, the analog signal is sampled at regular intervals. The sampling rate must meet the Nyquist criterion, which requires the rate to be at least twice the highest frequency present in the signal. So we are taking these samples and then we are giving the quantization. This quantization is the sampled signal is quantized, meaning the continuous amplitude values are mapped to a finite set of discrete levels. So we are giving, say, 8 levels in this case, 8-bit quantization. So every sample will have a targeted 0 to 7 category. Now from 0 to 7 we give them a code. For example, 7 will be known by 111, the 4 will be known by 100, the 1 will be known by 001. So every quantized signal is given now the encoding scheme, encoding number. So for example, you might have heard about Huffman coding and related codings. So this is the encoding being done. So first the sampling, that is small parts are taken. Every part is given a value from 0 to 8 in this case, and every 0 to 7 will be a digital code representation. This is the 3-level representation of the code. So this 111, 101, all these are actually the digital form of the original signal which was being sampled. So this sampling result in a digital conversion, which is ADC doing. Using multi-carrier modulation, the options are: the fading can be controlled, interference can be reduced, data speed can be increased. All three benefits are achieved. The correct option is all three benefits are achieved. This multi-carrier modulation, or MCM, is a spectral efficient modulation scheme which transforms the single high-speed serial signal to multiple parallel low-speed signals with different carriers, and then combines these signals to one serial signal for the further transmission. So again, a single high-speed serial signal, it converts to multiple parallel low beam signals with different carriers, and then it is combining these signal into one serial signal for further transmission. So what is the use of doing this? If you see the diagram also, this is a single carrier modulation, and that has been converted into the multiple low speed parallel signals. So these all parts which are been done, they have the central frequency also. That's why we can combine this signal to one serial signal for transmission. So for that, we can first of all efficiently use the spectrum. That is, MCM efficiently use the spectrum by allowing the overlap. Then we have the resistance to fading. MCM is more resistant to frequency selective fading than the single carrier systems. Then eliminating the interference, that means MCM eliminates the ISI, which is the inter-symbol interference, and the interfrequency interference IFI through this use of cyclic prefix. Then this is very suitable for the high data rates, because MCM is suitable for high data rate wireless communication. It is robust to narrowband interference, because this is robust to narrowband interference than the single carrier waveforms. It is efficient sharing of resources. This MCM allows for efficient sharing of resources in the frequency domain. Then we have the multiplexing. This MCM is allowing for multiplexing of multiple users in the frequency domain and spatial domain. MCM is used in several standards. That's why it's so important. For example, in DSL modems and digital video broadcast, DAB and DVB. Then we have the WiMAX and the LTE, 4th generation wireless networks. For example, IEEE 802.16, worldwide interoperability for microwave access, WiMAX, and the long-term evaluation, LTE also. FPGA stands for. So what is the full form of this FPGA? The options are fast parallel gate array, fast programmable gate array, field programmable gate array, none of the above. Now what is the correct answer? The answer is third one, which is field programmable gate array. Now this FPGA or field programmable gate array, this is what? Here you see this is the FPGA. So it's an integrated circuit that can be reprogrammed to perform specific function after it's being manufactured. So you can program it again and again to solve your specific purposes. That is why this field programmable gate array FPGA became so important to the electronics industry, because it is reprogrammable even after it's being manufactured. So the phrase field programmable in this field programmable gate array FPGA, it refers to an FPGA's ability to be programmed in the field or after the chip has been released from the manufacturer. So Xilinx, it's a technology manufacturer who have developed this, and it was first introduced, the FPGAs was introduced in 1985 for the first time. Now I would like to show you a peek hole view of this FPGA. So this part you see various programmable logic blocks, all these 4 which you are seeing in the broad view. And these are all the programmable logic blocks, the logic gates as you know. And these are the interconnection, these are the programmable interconnect. Through FPGA there are different programmable possibilities. Now if you want to make a counter, for example, this FPGA provides a very simple way of doing it. You can write a very simple code in VHDL, and this VHDL code can produce this counting facility using the FPGA. Equalizers are required to reduce. Now options are SNR, signal to noise ratio, attenuation, then BER, bit error ratio, or response time of the networks. Now these correct options are all of these actually. But if you have to choose the best one out of it, the answer will be BER or bit error rate. So what are equalizers in communication system? Now just assume that you have recorded a sound. When you are recording a sound, say for example a waveform will be formed. Sometimes there will be some distortion, some noise from the outside, some background noise distortion. So these are all the out of the box thing which can diminish the quality of your sound. For example, fur or sh, these are our words. So we need to equalize this whole waveform so that whosoever hear this sound is, say, hearable. So when we talk about the communication system, we have a transmitter, and the transmitted signal is passing through a channel. When it is received, it is not in that position where it can be used. So we need to use this equalization. So equalization or equalizers in communication system are used to reduce the ISI, inter-symbol interference, and the additive noise. So this ISI occurs when the transmitted pulse spreads out due to the channel's dispersive nature, causing adjacent pulses or the waveforms to overlap with one another. So the main function of the equalizer is to reconstruct the actual signal with the help of channel response and estimated signal and symbol. Now you see this is a very fine signal being sent, and now it has received and it is not equalized. The shape has changed. Just for the example, if you can just visualize it, now it has to be equalized, made into the original form. So this is the top 15 MCQs which we have covered in SDR, in cognitive radios and other radios. I hope you are benefited. The source is this one. You can just check it out. Thank you so much. Have a good one.